Hey, hope you're all having a good day. My name is Hector. We're going to go over question 61 for Video Explainer 5.2. So, astronauts in space weigh themselves by oscillating on a spring. Suppose the position of an oscillating 75 kilogram astronaut is given by x equals 0.3 meters sine of pi radians a second times t, where t is in seconds. What force does the spring exert on the astronaut at t equals 1 and at t equals 1.5? Note the angle of the sine function is in radians. Okay, so 75, our equation, 1 and 1.5. So I have the equation already written down here, right? So we basically need to build this. So I just kind of wrote a little graph over here of the sine. I don't really know how to depict this physically, but we're all aware with the sine function. This is basically going to be our sine function, our shifted transformed sine function for our position. So kind of just going through this, we basically build a force equation, right? So what is the force at a given time? So we have our independent variable I have written down here, of t, and then we're gonna obviously get our function in terms of ft, right? And then mass will be constant because we're not doing anything with relativity, so that would be nice. So we're going to use the Newton's second law to build out this equation. So basically we need to, figure out a way to include t in this equation, because you see, like, I have this dependent variable, but my independent variable isn't there, so I can't plug in anything. So I need to basically form this. So going back to our equation, we can remember that the second derivative of position is acceleration, or the derivative of position is velocity, and the derivative of velocity is acceleration. So the second derivative of position with respect to time will give us our acceleration. So we can kind of just write it down like this. Our force is equal to mass times acceleration, or the second derivative of our position with respect to time. So kind of just going through that derivation, it's just pretty simple. It's a regular old sine, so just sine to cosine to negative sine to on and on and on. And we left with this equation. Our second order derivative is negative 0.3 meters sine pi radians second times t, all times pi squared. Pretty much basic chain rule, just kind of going through the steps. So we can now just plug that in, and we can build our equation for f of t. So we get the mass is times, so this part right here is our acceleration, and so then we can simplify it down to make it a little bit prettier down at the bottom here. And we can just basically plug t in and go for it. So if we do that, first one, we get 0 newtons, sine of pi is 0. If you remember your unit circle, that should be, boom, pretty obvious, but yeah, sine of pi is 0, so it's 0 times 7.5 times pi, it all goes to 0, so all goes to 0. Plugging in 1.5 though, we get it's around 222 newtons, so that oscillation of from time 1 to time 1.5, so definitely a change in amount of force, because it's that change in acceleration. So yeah, really the trick to this question is just making sure you set your f equals ma correctly. Just, you need to make sure your f, equals ma. I don't have a better way to say that. And just that second derivative, I take the derivative once to get velocity, derivative twice to get acceleration. So if I want my acceleration, it'll be, and I'm given a position, I can just take 2 derivatives and it'll give me my acceleration. And yeah, I mean, that really just about does it. Really, yeah, it just kind of goes back to Newton's second law and just that relationship between different motions. The velocity is the rate of change of position, and the acceleration is the rate of change of velocity. That's where the derivatives come from as far as right now. And yeah, so I hope you'll have a good day. Bye.